Dark cones rise from the surface of Cydonia Calles, each crowned with a summit pit. Some appear remarkably fresh and undisturbed. These enigmatic features spark debate among planetary scientists. Are they cinder cones born from volcanic fire, or mud volcanoes shaped by subsurface flows? The answer remains elusive. Cydonia Calles occupies a transitional zone on Mars. To one side stretch the vast plains of Acidalia Planitia. To the other rise the ancient highlands of Arabia Terra. This boundary region preserves clues to multiple geological processes that shaped the red planet across billions of years. Fractured materials cover the floor of an impact crater in Arabia Terra. A channel cuts into the crater rim and exits on the opposite side. This configuration tells a story of flowing water. The lowest section of the crater floor hosts an unusual deposit. Together, these features point to an ancient lake that once filled this basin. Layered deposits blanket the surface, some displaying polygonal fracture patterns. Lake sediments typically produce such patterns as they dry and compact. The dramatic fracturing may record a catastrophic event. A sudden breach in the crater rim could have drained the lake rapidly, tearing apart the sediments. Layering cuts through an icy outlier in the southern hemisphere. This deposit stands isolated from the main polar cap. Each layer represents a chapter in the climate history of Mars. High-resolution imaging reveals the thickness and spacing of individual layers. Scientists can quantify the climate record preserved here. The critical question centers on comparison with the southern polar layered deposits. Does this outlier contain the same climate signal? Or does it tell a different story? The answer could reveal whether climate changes affected Mars uniformly or created regional variations across the planet over millions of years. A depression carves into the mantling deposit, echoing a similar feature photographed in 2011. That earlier observation captured possible summertime frost lingering in the shadows. Linear ridge structures cross the depression floor in an unusual pattern. Their origin remains unclear. Close examination can determine if frost persists here during the warmer months. The floor materials display distinctive textures that warrant detailed analysis. Understanding these features helps scientists decode the recent geological history of this region. Mantling deposits record atmospheric interactions over recent timescales. A mound rises near the center of a massive crater exceeding 5 kilometers in diameter. Its surface appears cracked and blistered like burnt skin. The formation mechanism poses a fundamental question for geologists. Viscous flow features surround the mound on all sides. Did these flows contribute to building the mound, or did they form independently afterward? The cracked surface texture demands explanation. Could material from the surrounding flows account for these fractures? The relationship between mound and flows holds the key. Solving this puzzle requires understanding the sequence of events that shaped this mid-latitude crater floor. Dune crests knife across a southern highlands crater, illuminated by a sun barely 5 degrees above the horizon. Shadows flood the landscape, drowning valleys between dunes in darkness. Only the sharp peaks catch the low-angle light. This extreme illumination transforms the dune field into stark contrasts. Each crest emerges as a bright thread against shadowed depths. The geometry becomes minimal and precise. Low-sun imaging reveals topographic details invisible under normal conditions. Scientists use such images to measure dune heights and slopes with precision, building three-dimensional models of these dynamic Martian sand seas. The equator facing slope of a deep trough cuts through Asimov crater. A thick sequence of materials once filled this crater completely. Sediments and lava flows may comprise this fill. Later, deep troughs carve the outer edges. Collapse over subsurface voids probably created them. Ice lenses slowly sublimating represent one explanation. Another connects to processes at Gale Crater, home of curiosity. Continued collapse could produce a central mound like Mount Sharp. Recurring slope lineae mark these slopes in summer. This southern trough destroyed the original southern crater rim, unlike at Gale. A small impact crater sits between two larger craters spanning 4 and 15 kilometers. Light-toned material brightens its ejecta blanket, remaining brighter than surrounding terrain. Darker atmospheric dust has not yet concealed it. The crater formed relatively recently, perhaps thousands of years ago. Its interior appears shallow and smooth. Light-toned rock also appears along nearby scarps and in strata at the 15-kilometer crater rim. This rocky layer predates all three craters. Different minerals produce distinct brightness and color. Water likely interacted chemically with native rocks to create these deposits. Banded ridges twist across Hellas, the largest impact basin on Mars. Furrows and pits accompany the ridges in complex arrangements. The surface flowed viscously like taffy, bending and stretching across the basin floor. Ridge orientations point along ancient flow directions called streamlines. Some ridges disconnect abruptly, breaking into blocky segments. Fragments appear offset from original positions. Either the flow rafted apart, or erosion exposed slices through complex patterns. What this taffy-like material consists of remains unknown. Rock and ice can both deform given sufficient time, pressure, and depth beneath the surface. Sediment layers stripe an east-facing slope in Tithonium chasma, running diagonally across the wall. Mars tilts at 25 degrees currently, similar to Earth. But calculations from Paris Observatory and MIT reveal chaos in Mars obliquity. Gravitational torques drove variations between 10 and 60 degrees. Higher obliquity produces warmer summers and colder winters. These climate swings left fingerprints in layered deposits. Uniform layer thickness suggests many cycles recorded over time. Afternoon light picks out subtle ridges. The layers deflect across these ridges, revealing ancient sediment geometry. Light-toned layered deposits climb the steep wall rock slopes of Coprates chasma. Valles Marineris harbors kilometers-thick sedimentary deposits along many of its floors. But these particular deposits defy the usual pattern. They cling to steeper terrain instead of settling on flat valley floors. Compositional data from CRISM reveals their mineral makeup. Stereo images allow scientists to construct three-dimensional models of the deposits. These tools help determine how the sediments accumulated in such unusual positions. Do they share the same origin as the thicker floor deposits? Or does their location point to a different formation process? Dark shapes and bright spots pattern a sand dune in the northern polar regions. The bright spots are carbon dioxide frost condensed from the atmosphere. Carbon dioxide dominates the Martian atmosphere and circulates seasonally. Mars temperatures drop far below Earth levels, allowing carbon dioxide to freeze onto the surface during winter. Spring warmth triggers sublimation. The frost transforms from solid to vapor, erupting in jets mixed with dust. These jets carve the dark features across the dune. The process repeats each year. HiRISE scientists monitor these seasonal changes to track year-to-year variations. Gullies carve down large mountains north of the Argyre impact basin, stretching over 6 kilometers in length. These dwarf the terrestrial landforms called gullies. Even by Martian standards, they rank as giants. The scale suggests massive erosional events shaped these features. Enhanced color views reveal only subtle variations across the gullies. The muted colors hint at similar compositions throughout the eroded materials. What force carved such enormous channels remains a question. Water, ice, or debris flows could each leave different signatures. Understanding these gullies helps decode the erosional history of the Argyre region. Thin condensate clouds drift across the surface at extreme altitude. The clouds appear to move 200 meters between sequential images taken 0.185 seconds apart. That calculates to over 1 kilometer per second. But clouds cannot move that fast. The MRO spacecraft traveled 603 meters along its orbit during the interval. From 260 kilometers altitude, this creates a stereo effect. The apparent motion reveals actual cloud height. Calculations place these clouds approximately 42 kilometers above the surface. Previous observations measured Martian clouds reaching 80 kilometers high. Earth cirrus clouds peak at just 12 kilometers altitude. Bright chloride deposits shine through darker overlying materials in this region. Salts form by evaporation of liquid water. When water containing dissolved salts evaporates completely, deposits remain behind. Scientists have identified over 600 locations that may contain chloride salts similar to table salt. Many resemble dried lakes on Earth called playas or salt pans. The bright deposits display cracks forming polygonal patterns like mud cracks. These patterns suggest the deposits formed as salty waters evaporated away. Studying these regions reveals when and how Martian weather conditions changed over geological time. Martian dunes creep across the western rim of the Hellas impact basin, driven by winds blowing east to west. Wind action slowly pushes sand across the Martian surface. Martian dunes form when wind blows in one direction for extended periods. These dunes sit downwind of flat-topped mesas. Extensive layered rock deposits underlie this area. Erosion carved away portions, leaving mesas behind. HiRISE first imaged this area in 2008. Comparing repeat images reveals dune migration speed and patterns. This data helps study current atmospheric conditions and sand mobility. The information also assesses hazards dunes pose to rovers. Chaotic terrain transitions into an outflow channel at this location. The origin of chaotic terrain and its connection to outflow channels remains poorly understood. Most scientists agree subsurface water bursting through the ground causes the chaos. The escaping water then carves channels as it flows away from the fractured terrain. The ground collapses into a jumbled mess of blocks and depressions. These features mark some of the most dramatic flood events in Martian history. Understanding how chaos forms helps reconstruct ancient water systems. The scale and violence of these events dwarf most terrestrial flooding. Cones with summit pits rise from the floor of Valles Marineris, resembling terrestrial cinder cones. Viking images first suggested volcanism here decades ago. Those candidates proved to be sand dunes under higher resolution. But these features stand different. They appear remarkably well preserved with only small impact craters. This indicates geologically young ages, perhaps less than a few 100 million years. Stereoanaglyph images confirm the cones stick up from the surface. Their shape clearly differs from impact craters. These may represent some of the youngest volcanic features on Mars. Small volcanic vents cluster adjacent to larger low shields south of Pavonis Mons. These features could be summits of heavily buried shields. Alternatively, they might represent smaller volcanic cones indicating a different eruption style. The distinction matters for understanding volcanic processes here. Low shields form from fluid lava spreading in sheets. Smaller cones suggest more explosive eruptions. Determining which mechanism operated reveals the evolution of volcanic activity. The region around Pavonis Mons hosts complex volcanic histories spanning billions of years. Each eruption style leaves distinct signatures in the landscape. An impact cuts into a steep massif in the Libya Montes region, exposing ancient lithologies. Bedrock alterations appear throughout the exposed materials, revealing chemical changes from water or heat. The Libya Montes mark the boundary between ancient highlands and younger lowlands. Impact excavation provides windows into subsurface geology. Scientists can analyze mineral compositions in exposed layers. Understanding these alterations helps reconstruct environmental conditions when rocks formed. The chemistry preserved in bedrock records interactions between rocks, water, and atmosphere across billions of years. A tongue-shaped flow extends down a mound near Ruel Vallis. The objective focuses on examining the flow structure at high resolution. The image may reveal a lateral moraine carved along the flow edge. Moraines consist of rocks and sediment carried and deposited by glaciers. If confirmed, this feature would point to ice-driven movement. The tongue shape suggests viscous flow over time. Material flowed downslope like thick syrup, conforming to underlying terrain. Understanding whether ice played a role helps reconstruct past climate conditions. Glacial processes require specific temperature and ice thickness to operate. Layers and exposed bedrock cascade down a cliff in West Candor Chasma, part of the vast Valles Marineris canyon system. The strata deviate from horizontal orientation throughout the exposure. Context camera images suggested crossed beds or lenses pinching out. These structures hint at the depositional setting when sediments accumulated. High-resolution imaging reveals the details needed for interpretation. Each layer records conditions during deposition. Were these underwater sediments settling in a lake, or wind-blown materials accumulating in dunes? The geometric relationships between layers unlock the past history of this region. Intact layers cut through the central uplift of Mazamba crater. Only 4 known impact craters possess such exposed layering in their uplifts. This layered material originated kilometers beneath the present surface. The impact raised it up during crater formation. Central uplifts form when compressed material rebounds violently after impact. The process excavates and exposes deep geology instantaneously. These craters provide windows into layers that would otherwise remain hidden forever. Scientists can study rocks from great depth without drilling. The layers reveal the vertical structure of the Martian crust in this region. Light-toned ridges cross this region, possibly created by pyroclastic eruptions. Pyroclastic flows deposit hot ash and fragments that cement into resistant layers. Modern erosion exhumes underlying flow materials. Multiple lava flows appear buried beneath other light-toned material. Wind has reworked this upper material extensively. The interaction between volcanic processes and wind erosion shaped the landscape. Volcanic deposits provide raw material. Wind sculpts and redistributes it. Distinguishing original volcanic features from wind-modified forms requires careful analysis. The ridges may mark flow boundaries or erosion-resistant zones. A possible volcanic cone rises north of Noctis Fossae, its summit hosting an impact crater. The feature serves as an analog to terrestrial cinder cones. Wind-blown bed forms surround the base, drawing material from somewhere nearby. The region consists of many overlapping lava flows. This supports a volcanic origin for the cone. Cinder cones form from explosive eruptions that eject fragmented lava into the air. The fragments fall back around the vent, building a steep-sided cone. The summit crater formed much later when a small asteroid struck the cone. This impact crater helps constrain the age of the underlying volcanic feature. The eastern half of Corozal crater displays seasonal frost across its slopes. Corozal sits inside a massive ancient impact crater in Terra Cimmeria. This crater hosts both active gullies and recurring slope lineae. The goal centers on monitoring seasonal frost evolution. Frost likely triggers gully activity when it melts or sublimates. As temperatures rise, frozen carbon dioxide transforms to gas. The escaping gas can mobilize surface materials, carving fresh channels. Tracking frost throughout the year reveals when conditions favor gully formation. Understanding the trigger helps predict where and when new activity might occur.